Okay, sorry about that, technical hiccups as per. So just to give everybody a little bit of background, who doesn't know, the Royal Geographical Society with the Institute of British Geographers is based down in London at Kensington Gore. It is a sort of learned society, professional body. It was founded in 1830, and it's responsible for lots of sort of scholarly geographical activities. There's involvement from academics, students, interested people. We have a community that sort of supports globally. And the idea behind RGS is that we're promoting geography. So a lot of the things that the RGS do is sort of informing about geography. There's lots of research grants, particularly for students and academics, but also for sort of people who are working out in the regional groups. And of course, we advise on policy issues and provide sort of fieldwork support, EDI training, things like that. If you're a young geographer, so if you're a sort of current student here in Bangor or online or at school, we have the Young Geographers membership. And again, it can help you sort of getting involved and sort of have access to the Geographical magazine, but also it might help you with university applications or job applications. I should just introduce Tina Lee-Jones, who's at the front waving. Obviously online people can't see, but Tina is the chair of the North Wales and Cheshire Regional RGS group. I think I've said enough, so I'm very quickly going to hand you over to Professor Tom Britworth, who's going to do the formal introduction before Iestyn takes the floor.
Good evening, everyone. So, yeah, I'm here to introduce our star speaker tonight, Iestyn. So Iestyn first came to the attention of Bangor University way back in 2008. And it was because at that time, Bangor University soccer team were actually riding really high in the North Wales League. Wins all that season, and then they went down 5-3 to Porthmadog. And according to the Daily Post, they were guided to victory than none other than Iestyn Woolway. So about this time, Iestyn actually started in ocean science as a student. He did his BSc in ocean sciences, achieving a first-class honours. And in 2011, he moved on to an MSc course, which is actually run for many years here in Bangor, called Physical Oceanography. And that happened to be the year that the UK Natural Environmental Research Council selected that MSc course as one of their big impact success stories. And this was reported quite widely. And I've got quite an interesting report here from the local press about this fantastic MSc course. When the Wales rugby team were at their zenith, sometime before the recent matches, unfortunately, there was a newly created myth of a production line producing star rugby players hidden somewhere in the valleys in South Wales. While at the other end of Wales, there continues to be a lasting success of producing excellent oceanographers for the very real world. At this stage, it was 45 years. Now, obviously, it's 57 years. And they went on to interview some of our students at that time. And one of them was a Iestyn Woolway of Porthmadog. And he said he hoped his career would eventually take him to the Arctic, which is an area he'd had a long-standing fascination with. And in particular, he was very keen on looking at climate change in the Arctic and how it affects the globe. Well, Iestyn went on to graduate from the MSc course to do a PhD at University College London. He then went on to win several prestigious research fellowships before returning to Bangor last year. And his excellence was recognised earlier this month when Iestyn was actually honoured by the Learned Society of Wales through the award of one of their 3 Dilwyn medals. And these medals are awarded to celebrate outstanding early career researchers. So tonight, it's a great pleasure to introduce Iestyn, who's going to be talking about his groundbreaking climate change work, which now not only covers the Arctic, but also other areas of the planet as well. So over to Iestyn.
Okay, thank you, Tom. Warm welcome, everyone. So My name is Iestyn Woolway. I'm a climate scientist based here at Bangor's School of Ocean Sciences. And my research looks at how climate has changed. So how the climate has changed in the past. I try to predict how it will change in the future and the impact that this has on the Earth system. The way that I do this is I analyze data from what we call sentinels of climate change. Sentinels of climate change are kind of indicators of the impact of climate change and how we can use them to understand how the climate is changing. So I'll provide a bit more information about sentinels in a second, but I thought I'd begin by briefly describing what climate change is. So climate change is a large-scale, long-term shift in the planet's weather patterns or its average temperature. So climate is basically the average weather in a place over many years. And climate change is a shift in those average conditions. So for example, if we think of the temperature in Bangor today, that would be the weather. If we think of the temperature of Bangor over the past 20 years, that would be the climate. And climate change would be a comparison of those 20 years against some 20 years in the past. Now, natural factors influence our climate. These include the way that the Earth wobbles in its orbit around the sun. It includes the way that it rotates off its axis, and it includes things such as natural volcanic eruptions and so on. All of these things influence our climate. However, since the mid-1800s, humans have begun to burn fossil fuels such as coal, oil, and gas for energy. This is known as the Industrial Revolution. And by burning these fossil fuels, we have emitted large amounts of greenhouse gases, so carbon dioxide, methane, and so on, into the atmosphere. Over time, large quantities of these gases have built up in our atmosphere. This is a figure showing those changes in carbon dioxide concentrations since the year 1960 till the present. So this figure demonstrates CO2 concentrations from the Mauna Loa Observatory located in Hawaii. It's an observatory that's situated at approximately 3,400 meters above sea level. It's a long distance away from significant pollution sources. And it's one of the best indicators that we have of our impact on the atmosphere and the climate. So what this figure shows along the horizontal axis is the year, so 1960 till the present. And on the vertical axis is the carbon dioxide concentration in parts per million. What you can see from this figure is one, the seasonal variations in carbon dioxide in the atmosphere, and two, a long-term trend, this long-term increase in the amount of carbon dioxide in the atmosphere. The data from Mauna Loa is shown in blue. You can see the seasonal variations, and from two additional observatories shown in red and in yellow. Now, these greenhouse gases that we've emitted to the atmosphere, they form what we can call a blanket around our planet. And this blanket essentially traps heat from the sun and causes the Earth to warm up. So the more of these gases we have, the quicker the Earth warms. High levels of greenhouse gases in the atmosphere are the leading cause of increasing global temperatures and the main drivers of climate change that you hear about on the news every day. So on average, the world has now warmed by over 1 degree Celsius since the late 19th century. So this is a global average figure. The way that we know this is we have millions of measurements from hundreds of thousands of meteorological stations situated from all over the world. If we take in the information from all of those meteorological sensors, we have a graph that looks similar to this on the screen. So this is the temperature, the annual average global temperature anomaly figure. So on the horizontal again is time, and the y-axis here is the temperature anomaly. So the temperature anomaly is the temperature difference of any point in time, so each of these vertical bars, relative to pre-industrial levels. So in this definition, pre-industrial is the period 1850 to 1900. So the figures that are shown in this figure represent the difference between that year and this base period average. What you can clearly see is the large amount of red on the figure on the right-hand side, which means that today we're experiencing rapid warming and an increasing trend of global temperature rise. However, the amount of temperature increase that we experience in the world differs globally. So this is obviously a global average. So if you look at specific parts of the world, the temperature trends will be very different. In the high Arctic, we'll see much greater temperature increases. And in the tropics, we see considerably less. In Wales, we have measurements dating back to approximately 1884. And this is the temperature anomaly time series for Wales up until the present day. Again, the x-axis, horizontal axis here is time, and the vertical is that temperature difference from a base period average. The key thing here, if you look at the amount of blue and the amount of red, you can see in the most recent years, we're very much on the warmer part of the spectrum. So in 2020, 2021, 2022, temperatures in Wales have been increasing above this 1 degree temperature anomaly threshold. Okay, so climate change is not just seen in these temperature records and these measurements that we have of temperature from different parts of the world. We can also see it from other indicators as well. So sentinels of climate change refer to these indicators or these markers that provide evidence of the impact of climate change. So basically, these sentinels are critical for those regions in the world that we don't have those measurements. So it can either be to fill the space in space or in time. So we don't have measurements everywhere and we don't have measurements going back through time. So sentinels are what we try and use to fill those knowledge gaps. One example of a climate sentinel is the cherry blossom season. It's Japan's traditional sign of spring. So in this region, records began approximately 1200 years ago. And on the right-hand side, I show one of the longest time series available of the peak bloom day of year of the cherry blossom. This is from Kyoto, Japan, and has data from the year 812 to 2021. So on the horizontal axis is time going from the year 800 to 2021. And on the vertical is the date of the year. So it goes here from March 11th till April 20. Each point in this figure represents a peak bloom day of year. And the kind of the horizontal or the solid line represents a moving average. So it's a 20-year or so moving average. So two things that you can see from this figure is one, the large variability in that peak bloom day of year. So 1 year is very different from the next, and it's kind of very sporadic in its long-term change. But secondly, when we isolate the climate signal, looking at this solid line, we can see that up until the time of the Industrial Revolution, it was kind of stationary, kind of stayed relatively flat. And thereafter, it followed a kind of a steady decrease, meaning that the peak bloom day of year was occurring earlier. And this is a direct response to climate change. So if the world is getting warmer, this happens earlier. So the work that I do is try to find these climate sentinels and analyze data from them to understand how the climate has changed. And one of the ways, or one of the sentinels that I often use is lakes. So lake ecosystems, which are distributed from all over the world, they're located everywhere, they're highly sensitive to climate change. The three key features of lakes that I look at to identify these climate patterns include changes in ice cover, so when and if a lake freezes. Two is its water level, so how the volume of water in a lake changes through time. And thirdly, direct measurements of its temperature. So how warm are those water bodies becoming and how warm have they been in the past? Each of these three indicators follow changes in the climate relatively closely. So to begin, I'll talk about the work that we've been doing here at Bangor University and also with my collaborators from abroad looking at lake ice and how lake ice has changed over time. So lake ice itself is a very sensitive indicator of climate change. So it closely tracks changes in air temperature. So you can imagine lake ice forms when air temperatures drop below 0 degrees Celsius and stays below 0 degrees Celsius for a period of time. So if the air warms, lake ice doesn't form. One of the key things about lake ice as well is that people have used lake ice for centuries. So we have some information of these activities that people have used lake ice for going back centuries, even 1,000 years. Some examples include some regions in Northern Canada, for example, Scandinavia and so on. Hockey. People use lake ice for recreation. They host hockey events, they host ice fishing events, competitions, and so on. And each of these, we get some indication of how these events have changed through time. Also, in many northern regions, lakes are actually used for these large transport trucks. So when these lakes freeze in winter, they essentially create highways going along them to connect remote communities to travel from one to another, to transport material, medicine, and so on. In some of the regions, lake ice has been important for religious purposes. So I'll provide an example in a second of Lake Suwa in Japan. But also there are other instances in Europe, for example, in Lake Constance, on the border of Switzerland, Germany, and Austria. In terms of the data that we have showing changes in lake ice cover, this is one of the best examples that we have of a continuous lake record. So this is the duration of ice cover in 2 lakes in Wisconsin in the USA. So these are Lakes Mendota and Lake Monona. The horizontal axis here shows the year going from 1850 till 2021. And the vertical axis shows the duration of ice cover. So this is the number of days in a year that these 2 lakes froze. 2 key things that we can see from this figure is, 1, the lake ice duration varies quite dramatically from one year to the next. It can be high in one year, followed by a low year in the next. But 2, we see this long-term declining trend in the duration of ice cover, where during the start of the observational record in 1850 or so, the duration of ice cover was approximately 120 days. But in the most recent years, in 2020, 2021, the duration of ice cover was as short as 80 days. And in some extreme years, the duration of ice cover dropped to less than 1 month. So we also see these changes in river systems. So we have some of the longest observations of ice cover changes in rivers. This is an example of the Torn River, which is located between Sweden and Finland. So we have direct measurements from this site from 1693, so the year 1693. And those long-term changes are shown on the left-hand side here in the figure. So we have year, horizontal, and then we have the ice breakup date on the vertical axis. So the ice breakup date is essentially the last day of the year which ice was present. So this is the day that the ice thawed. Day of year refers to the number of days from January each year. So January 31st would be day of year 31, February 1st would be 32, and so on. So what you can see here is from the year 1693 till the present, we have this gradual long-term decline in the ice breakup date, meaning that the breakup is occurring earlier and earlier. But secondly, what we can see is at the timing of the Industrial Revolution, or shortly thereafter, we see a break point in this ice breakup day of year, meaning after this date, the ice breakup was occurring faster and faster, and this is continuing till the present. One of the best examples, and one of my favorite examples of ice data, is from Lake Suwa in Japan. So every year since 1443, priests who have lived at the edge of Lake Suwa have carefully recorded the date of ice formation. So the day of year in which ice forms and how long it would form for. This is one of the longest continuous records of ice cover that we have anywhere in the world. Now you ask, why were people measuring or recording ice cover going back to 1443? Now, in this particular instance, it was to monitor the appearance of a sinusoidal ice ridge, which is known as the Omiwatari, which I'm sure I'm mispronouncing. It's shown on the right-hand side. So this is a photo of this Omiwatari. And the priests believed that this is the appearance of, the Omiwatari is a message from God. They believe that the Omiwatari forms by the footsteps of a male god when he would cross the lake to visit a female god in her shrine on the other side of the lake. So this has great religious meaning for people in this region. Each year when this Omiwatari would form, they would have a ceremony, and they would measure things such as, one, the height of these ridges, the direction that they would point, and their length, and so on. And they would record them all in these, essentially what are logbooks. They would write this information on rice paper and other forms. And today we can actually use these measurements or these observations to see how the ice cover in this part of the world has changed. So in this figure, I show the vertical axis is the number of years with no ice. So the number of years when the lake did not freeze or the Omiwatari did not appear. The horizontal axes are essentially 50-year bins where the number of no ice years have been reported. So some of the key take-homes from this figure and from the Lake Suwa data set is that during the first 250 years of the ice record, the lake froze every year, except for approximately 3 isolated events. As we get closer and closer to the near present, the number of years with no ice is slowly increasing. So up until the year 1999, we see that the number of years without ice is about 1/5. Since the turn of the millennium, the lake has only frozen 7 times. And some of my collaborators from Canada, so Sapna Sharma in particular, has been using this data and trying to predict what this means for the future and how will these no ice events emerge as we move throughout the 21st century and the different climate change scenarios. And some of the results that they found was that as the climate warms, Lake Suwa will progressively transition to experiencing no ice cover. And as we move to the mid-21st century, so the second bar from the right here, the number of years without ice will increase even more. And then by the end of this century, the lake will not freeze at all. So even as early as the year 2040, which is less than 20 years away, the models that we have predict that this lake will not freeze. And obviously that has large implications for the religious beliefs and the ceremonies and so on in this region. So Lake Suwa is not an isolated instance in terms of experiencing a loss of lake ice and transitioning to a permanent ice-free state. So a lot of the work that we've been doing is combining as many observations that we have for lake ice cover, either being from satellite measurements, direct measurements, with machine learning models to predict how these patterns vary globally, or in particular across the Northern Hemisphere. What this figure shows, we're looking at an aerial view of the world. So this is looking above, down at the Northern Hemisphere. The blue-green color refers to lakes that reliably freeze every winter. So these lakes always experience ice cover. Orange means that lakes that no longer freeze every winter. So these can freeze in some years and others, they don't experience any ice cover. Currently, there are approximately 15,000 lakes that don't freeze every winter. But as the climate warms this century, we see the lakes that don't experience ice every winter grows. So what we have in this animation is going from current conditions to a high level warming scenario. We have the number, you can see the orange regions expanding further north, which means that the number of lakes that don't freeze every winter will increase and increase. Under the high-end emission scenarios, which are kind of the high warming rates, we estimate that approximately 215,000 lakes will no longer freeze every winter this century. Those lakes that we expect to experience the most change are those deep lakes, but also those in southern or coastal regions. So these include Lake Constance in Central Europe and also Lake Superior in North America. So Lake Superior is a huge lake, much bigger. So the Lake Superior system, which encompasses Lake Superior, Huron, Michigan, and so on, is a vast lake system, much greater in size than the United Kingdom. These lakes may lose their ice by as early as 2060. So just to look back at why is ice melting earlier and freezing later in lakes? So the primary culprit is climate change. It's the increase in greenhouse gases, which is causing air temperatures to rise, and as a result, making it harder for lakes to freeze. But also local weather. This is not just temperature, but also changes in rainfall patterns, so precipitation rates, and changes in snow cover. So precipitation and snow cover are two key factors that also influence lake ice cover. And all of these things contribute to what we've seen in the past and what we expect to see in the future in terms of the changes in lake ice cover. So the implications of losing lake ice. So on one side of the argument, they have direct implications for the ecological dynamics of these systems. But in terms of what we can see, they will have a direct impact on how we use lakes. So use lakes recreationally for ice skating, ice fishing, and also for these transport routes that I mentioned for northern communities. So a lot of the work that we've been doing over the past 2 years or so has been looking at what are the impacts of losing lake ice in different parts of the Northern Hemisphere, and specifically looking at how transport routes in Northern Canada will be impacted by the loss of lake ice. So ice needs to be of sufficient thickness to support different types of transportation. So for example, for large transport trucks, lake ice needs to be 107 centimeters thick. But instances where this will be, where lake ice this thick will be present in the future will be very minimal. So changes in lake ice cover also has a direct impact on another climate sentinel that we use often to look at climate change, and that's the temperature of lakes from around the world. So if we have less ice in winter, it has a knock-on effect on summer water temperatures in lakes. So an earlier ice loss means that lakes can heat up more during the season. So they're exposed to atmospheric heating throughout the larger part of the year. So for example, if a lake was historically frozen for 6 months and is now only frozen for 3 months, it has that additional 3 months of heating from the atmosphere, causing their surface temperatures to rise. We're part of something called a global lake temperature collaboration, which is a global effort to collate as much information as we can from lakes around the world, looking at how their temperatures have changed in the past. These include measurements taken by hand from citizen scientists, from research scientists from as early as 1910. So we have some measurements from, for example, some lakes in Austria, which started in 1910, 1908. And then we have a large array of temperature observations from different parts of the world, which have made the most of high resolution monitoring stations or even data collected from satellites. So this is a key figure in terms of how lake temperatures are changing and how they have responded to historic climate change. So this figure shows, obviously this is the map of the world. each point represents the location of a lake. The color represents its warming rate. So this is the rate of change in temperature in lakes worldwide. Red means that they're warming, blue means that they're cooling, and then the darkness of each color represents the magnitude of that change. So dark red means that they're warming more, dark blue means that they're cooling more. In this study, analyzing these 350 or so lakes, we found that 90% of lakes worldwide have warmed during this study period. So the period of this study was from 1980 to 2009, and 90% of those lakes have warmed during this period. Obviously, this was back in 2015. This was a big paper that was published by Catherine O'Reilly in 2015. It's been heavily cited. But in recent years, so we published a paper looking at even more lakes. So now that we have better processing methods for analyzing satellite data, we've been able to increase the number of sites that we can observe from these 350 to over 92,000 lakes. This is a paper that was published a month or so ago. And this shows, similar to the other figure, it's obviously a map of the world. And the different colors again represent cooling in blue, warming in red. And we immediately see the vastness of the red color in this figure, meaning that during this study period, the vast majority of the lakes worldwide were warming. So among these 92,000 lakes, only a relatively few were experiencing a cooling trend. Now, an interesting thing about lake temperature is that it doesn't solely follow changes in air temperature. There are also other factors that contribute to its rate of change. So for example, changes in wind speed in particular parts of the world can lead to lake cooling or even lake warming, depending on the direction of change. And this is what we think that we see in this region in kind of like Siberia there. There'll be changes in wind speed. So if you have an increase in wind speed in a region, it can lead to lake cooling. A decline in wind speed can lead to lake warming. It can also be changes in solar radiation. So changes in cloud cover, for example, can impact lake temperatures. And what this figure does is try to encompass all of that information into a global map of lake temperature trend. So in summary, for lakes, the air temperature increase that we've observed over the past several decades is the dominant driver of lake temperature change. Patterns of solar brightening and dimming, these are when the amount of solar radiation that hits the Earth's surface is changing. Brighter, meaning more radiation, or dimmer, meaning less radiation, can have a strong impact. And this global phenomenon known as wind stilling, where we have a global decline in wind speed from around the world. Now, as lakes warm, water temperature increases, evaporation rates increase. So one of the direct impacts of a warmer water body is that evaporation rates increase. As evaporation rates increase, it can lead to a decline in water levels. So if you lose water via evaporation and that water is not replaced by either rainfall or inflowing water, lake level can decline. And this takes us to our third climate sentinel, which is lake level or lake volume. So similar to ice cover and lake temperature, we have great observations for water level from different parts of the world due to its importance. So water in lakes is used for drinking, hydropower, and also shipping. So this might seem strange to us here in the UK because we have very small lakes, but in other parts of the world, we have massive lakes and they have these large cargo ships that transport material from one side of them to the other, Lake Superior being a good example. Historically, we have measurements from like gauges. So at the side of the lake, there would be like a dial where you would see what the level was in a particular day. You'd go and record that and you'd come back the next day, the next month, and you'd quickly build up a time series of changes. Nowadays, we have data from satellites. So we have numerous satellites currently orbiting the Earth. they take measurements of the height of different surfaces. So for example, in terms of water level, we have satellite altimetry, which essentially measures the time that it takes to send a radar pulse to the Earth and measures how long it takes to come back. We know how long it should take to go through different types of material, water being one of them. And using these data, we can get a detailed view of lake volume or water level changes across the world. So this is an example of 3 satellite images taken from Lake Popo in Bolivia. So this lake is highly susceptible to climate change. In these 3 images taken from three separate years, April 2014, 2015, and then January 2016, we see dramatic changes in the shape of this lake, meaning a change in its water volume. So in this particular example, the amount of water in the system is dependent on, 1, the amount of water that's extracted from the lake, so the use of agriculture, for example. 2, the low amounts of precipitation in this region, precipitation being rainfall. And 3, it's those high evaporation rates due to a warming of the water. This lake experienced historic lows in 2015, 2016, as shown on the right-hand side here. 2 other satellite images, this time of Lake Mead in the USA. So Lake Mead, also known as Hoover Dam. Here I show 2 satellite images, one in 1989 and one in the year 2019. So Lake Mead is one of the largest artificial lakes in the world. It's located approximately 25 miles east of Las Vegas, California, Nevada, and it's formed by the damming of the Colorado River. Now, between these 2 satellite images, one again in 1989 taken from Landsat satellite, and the second in 2019 taken from Sentinel-2, another satellite. 2 key things that you can see from this figure is, I don't know if the pointer works. On the left-hand side, you see the size of Las Vegas to the east. So on the left-hand side, if you notice the size of Las Vegas and compare it to the size of Las Vegas in 2019 on the right, you see this dramatic increase in the size of the city. At the same time, what you can see is a reduction in the size of that lake. So essentially, as more people in this region depend on this freshwater source, the water levels are declining. Now, obviously, it's difficult to see from these 2 satellite images how things have changed because you're not really comparing like for like. It could have been an extreme year in one versus the other. So using these satellite data, we can look at very detailed time series changes of water level in this lake or in any lake from around the world. What this figure shows on the horizontal is the year going here from 1995 till 2021. And vertically it shows the water level in meters. So we can see going back to 1995, 96, 97, 98, the water level was relatively high, but ever since we see this long-term declining trend in lake level. Some lakes are even disappearing altogether. So these are 2 images, 2 photos that were taken from a collaborator of mine, Professor John Small from Queen's University in Canada. He would go to these high Arctic lakes every year to take measurements of ecological things. And he'd take some samples back to the lab and look at how they're responding to climatic variations. When he went back in 2006, the lake had disappeared. So he'd had these measurements over many, many years, and due to some abrupt climatic changes, the lake had disappeared this one year. Now, not all lakes are disappearing or even shrinking in size. Some are actually growing. In some high altitude regions, so the Tibetan Plateau being an example, so this also known as the Earth's 3rd pole. So it's a high mountain region, more than 4,000 meters above sea level. This region is also experiencing considerable climate change. In this particular region, what we are seeing is due to a warming of the air, the glaciers in the region are melting. All that glacial water is rushing into the water bodies, into lakes, causing their surface area to expand. When we take all of the satellite images that we have and bring them all together, we end up with this complex kind of mosaic of water storage trends from around the world. So on the top left, this shows a world map showing how lakes represented by each point are changing in terms of the volume of water within them. So red means that they're losing water, blue means they're gaining water, and purple means that there are new water bodies being formed. So you see these instances, particularly in places like China, where new reservoirs are being built. And this is the type of information that we can get from our satellite measurements. So I show, again, two images here, which will keep rotating. One is the formation of a new dam in Sudan. This is the right-hand side figure. So if you look closely at the bottom of that image, you will see now the dam being formed, and then over the following years, the dam, the reservoir is filled with that water from the river. The second example, just to the left of that, is the disappearance of the RLC. So this is one of the most well-known examples of water level decline in any water body around the world. This used to be one of the largest inland seas, lakes in the world, but due to the extraction of water from this lake, the lake is now only a remnant of its former self. Overall, what the data suggests is that over 50% of the largest lakes in the world are losing water due to either climate change or unsustainable human consumption. Now, this is my last slide, and it's kind of like the take-home message, I guess. So there are more than 170 million lakes in the world. We can currently observe about 92,000 of those. So although the number 92,000 seems like a lot, we're only really seeing a very small part of the picture. And the work that we're doing now is trying to improve our satellite processing capability to see many more of those lakes. The problem that we have is that many of those lakes, so 90% of the lakes in the world, are very small. So what you can see with satellites is quite limited when you're looking at very, very small systems. And one of the important things to consider is that many countries that have lots of lakes don't have direct meteorological measurements. And what we're trying to do is to fill that gap in our knowledge by using these sentinels, in my case, lakes, to look at how climate change has changed in different parts of the world, again, in space and in time. And with that, I thank you very much.
Thank you very much for a great lecture. I'm just going to stand here and then I can come and see you. So Iestyn, thank you. It's been brilliant. Thank you to Tom for helping to put on the lecture. Thank you to Bangor University. Thank you to all of you for coming. But have you now got questions? And online, we're ready for questions too. So please come and let us have your questions. If you just write your questions in the chat box, I'll ask.
Thank you, Iestyn. That was so cool. And everyone should want to work with you. I do. I'm Young Len, in case anyone's wondering, from Ocean Sciences. So we know that sea ice, as its decline, has had an impact on the atmosphere. And we think that this is really important for probably exacerbating Arctic climate change as well. So do you see the same sorts of feedbacks from the lake ice and the atmospheric system?
Yeah, we do. So for lakes, it's less of a global impact. It's more of a local impact. So in regions such as North America, for example, there are lake snow effects. So if lakes freeze or if they don't freeze, it has an impact on snow precipitation patterns in the region. Chicago, for example. So we do see those. I don't believe anyone's looked at like long-term trends and those sorts of things, but their impact on snow and other stuff. Yeah.
Any more questions now? Walked all the way up here.
While we're waiting, What is the effect with the dams coming and the flow of the water? Is it having a huge effect down the line?
Yes. So it has two effects really. So one, I'm not sure if it's the biggest effect, but when these dams are created, you see, like I mentioned then, you see an impact that it has on the local weather. So in some regions, like Three Gorges Dam, for example, massive systems that have been created, you actually see an imprint of that vast volume of water on local temperatures and so on. But obviously, in terms of the ecology, in terms of the organisms and so on, lakes, rivers, they're connected. If you stop that system, one flowing to the other, it has an effect on them as well.
Lovely. Thank you.
Hi, Iestyn, great talk, thank you. I had a question, was about, I guess I was wondering whether there's any evidence that nearby land use change is having an effect as well, particularly for small lakes, because I've been reading, this idea that we can reduce city temperatures by planting more trees. Obviously, around a lot of lakes in the world, they're cutting trees down and urbanizing areas. So is there any evidence that that is adding to the problem of the warming air temperature from the sun as well?
Yeah, so I'm not sure directly about that, but what I can say in terms of land use is the effect that it's having on the quality of water in lakes. So agriculture, use, fertilizer, and so on. Once these things flow into lakes, we have a serious problem in terms of the amount of algal blooms and the severity of those algal blooms. So if you ever go to a lake and you see it green in color or so on, it's because of these fertilizer inputs largely from nearby land. So that's one of the biggest impacts that we see of the interaction between lakes themselves and land use in their regions.
Doug Walters was saying what a great talk it is. And are there some parts of the world where it's easier to study the lakes than others?
Yeah, so the easiest places are, well, today, with the use of satellites, is those regions that have the very large lakes. So we can see them in high detail. In terms of historic climate change, before satellite measurements, it's North America, Europe. These are the places where we typically have those long time series that you really need to understand the impact of climate change.
Okay. April Bishop, can chemical reactions such as human purposely realizing into the clouds, could that be a sentinel?
I am not sure.
There you go. We might come back to it at a later date. Steve Blight, do you have any data for lakes in Snowdonia?
Not in terms of long-term changes. Unfortunately, we don't. We have some monitoring stations on lakes, for example, in Bala. So there's a lake, Llyn Tegid, which Natural Resources Wales have a monitoring station where they measure hourly, minutely temperature, oxygen, and so on. But to my knowledge, we don't have any long-term records. The closest that we have here from the English Lake District in Cumbria.
Okay, super, thank you. And Sophia, what are your thoughts on the current lake water level trends based on your experience? Would you say that lakes are disappearing due to climate change?
Yeah, so the volume of water or water level in a lake, it's a delicate balance between how much water we extract for agriculture, drinking water, so on, how much is replaced by either rainfall or the amount of water that flows in from rivers. Like I showed in one of the slides, we see that approximately 50% of large lakes in the world are reducing in size. The other 50 are either increasing in size or staying the same. So in terms of lake level, there's no concrete answer in terms of saying that they're all declining. It's kind of a mixture of some are increasing, some are disappearing.
Thank you. Oh, another answer.
Hi, Iestyn. Thanks for the talk. I really enjoyed it. I was interested in, all the statistics it's showing that there's increases or decreases, and the evidence is really overwhelming. But I wondered if anyone's looking at those lakes that aren't changing in some of those metrics, and if they are you able to predict why they're not changing? Because maybe, from a coral reef perspective, another sentinel for climate change, people are now identifying bright spots and looking at what makes a really healthy coral reef, really healthy despite all the global impacts. I wondered whether that kind of work has been done on lakes.
Yeah, definitely. So in terms of the two lake sentinels that react directly to climate change, so those are like ice and temperature, we know what the main drivers are. So there'll be changes in either air temperature or wind speed, solar radiation. So in regions where you see that they are not changing as you'd expect, they typically are in regions where the wind is changing in a different direction to how it is normally, like declining or so on. And I think I mentioned it earlier, it's to do with solar brightening in some places as well. So many different factors. People are exploring these, but obviously when the numbers of lakes increase to 92,000, it's very difficult to then isolate the drivers in each one of them. But yeah, it's a good point.
Has anybody else got any questions? Gentleman there.
Hi, Iestyn. Thanks for your talk. So from your talk, I learned that some lakes, they are losing their water due to its warming. But do you consider that there are also many lakes, they are connected with rivers? And those rivers, they comes from the mountains. So it means that when the world is becoming warmer and warmer, so they have more inflow due to the melt of ice. And then, so this kind of things, like it will increase the water level. When you do your analysis, do you also consider this kind of this part of the water?
Yeah, so one of the key things that we do more so recently is the attribution of change, and this is looking at the direct drivers of different variables, and one of them is rivers, like you said, replenishing that water into lakes. And we see in regions where, for example, dams are being created and that replenishment of water does no longer occur, we see that the lakes are responding as you'd expect. But also with the glaciers, like you mentioned in the Tibetan Plateau, as they melt, they directly feed into those systems, and the water is either replenished or it causes the lake to expand quite dramatically. Thank you.
Any more questions? That's it. Yeah. Oh, well, thank you so much for your talk this evening. Thank you, everybody, for coming today. If you've got any questions, we'll be here for a couple of minutes afterwards. Come and talk to us. Thank you very much. Thanks so much for everything.